In this unit, we have had a lot of practice drawing Lewis structures. And I have an example right here on this cover page. And almost every bond that we've drawn was a covalent bond, which means that the electrons between those two atoms are shared. They are not transferred as they are in an ionic bond. Well, the sharing of those electrons, in this case, 2 electrons for a single bond, the sharing of those 2 electrons are not typically equal. Typically, those electrons are closer or surrounding one atom more than the other. And that is based on the atom's propensity to attract those electrons. That is called electronegativity. And we are going to look at the electronegativity of several elements and decide whether that bond is going to be mostly covalent. Is that covalent bond what's called a nonpolar covalent bond or a polar covalent bond? Using these electronegativities as well, we can include ionic compounds, and we'll see what those atoms' electronegativities are that participate in ionic bonds. Okay. Ultimately, what we want to be able to do is categorize bonds as nonpolar covalent, polar covalent, or ionic bonds. But this is important also for our ability to draw Lewis structures. For instance, if I have PO4 3 minus, okay, we have to identify the central atom, okay, and maybe it's easy. It's easy to see that, hopefully easy to tell that the central atom should be phosphorus. So this is pretty obvious that phosphorus is central atom. Okay. It's typically, in these cases, it's the one that has a single atom, element, I mean, and you have multiple copies of a second element, like oxygen. So you would put the P in the middle and oxygens around it. But there are other examples that are not as easy. For instance, OCN. Now, we shouldn't assume just because C is in the middle that it's the central atom. Okay, when it's not obvious, like PO4 3 minus, then you're going to pick the atom that is the least electronegative. So the least So there's that term, electronegative. Least electronegative atom is usually the central. So this is not so obvious. Let me give you a working definition for electronegativity. Let's say the propensity or the ability to attract electrons. But really, the way I use electronegativity is it's within the context of a bond. So the ability to attract electrons of a covalent bond. The higher the ability, the higher the electronegativity. And we're going to see a table called the Pauling electronegativity table in just a bit. You don't have to memorize these numbers, but there are a couple of elements that you want to know about. But before we get to that table, it's very closely related to electron affinity. If you recall on your periodic table, electron affinity increases from the bottom left to the top right. But don't look at the halogens. So here are the halogens. So if you think about electron affinity, fluorine has the highest electron affinity. We've talked about electron affinity in a previous unit. But just as a reminder, highest, sorry. Just as a reminder, it is the energy released when an atom gains an electron. The higher the energy released, the more likely that atom will gain an electron. So the energy released when gaining an electron. Well, electronegativity has the same trend. Again, this is increasing. And again, we are going towards F. Okay, let me show you Pauling's electronegativity table. This one's a little bit of a fancy one. It's three-dimensional. But the numbers that we want to look at, now don't worry too much about the units of the numbers. It's a relative scale. It's a relative scale. So this is Pauling. Okay, for Linus Pauling. Pauling electronegativity table. Or chart. All right, the elements that you want to be aware of. Fluorine is the most electronegative. Again, don't worry about the units. If you recall, the energy released, those units are going to be typically kilojoules per mole. But electronegativity, it's going to be a relative scale. And you're just looking for the highest number to figure out the most electronegative atom. In your notes, I would put here fluorine is the most electronegative atom. And I would say oxygen, okay, 3.5 is the second most. Do we have any other 3.5s anywhere? Yeah, I don't think so. So fluorine is 4.0, oxygen is second most. Remember our trend, right? Our trend is going to the northeast. Fluorine is the most electronegative, oxygen is the second most. In general, as you go down the column or the group, electronegativity gets smaller. What does this mean? This means that if you have a bond between, let's say, F and H, okay, hydrofluoric acid, it's a covalent bond, but the electrons of that bond are going to spend more of their time around fluorine or closer to fluorine than they do around hydrogen. And just for completeness, we should be drawing all the valence electrons, whether they occur in bonds or as lone pairs. Okay. There are symbols that we could put to indicate that it's an unsharing of electrons in the covalent bond. One way is to draw partial charges using the lowercase delta. Delta negative, delta positive. Why negative? Because it's drawing electrons towards it. The other way that we could show this is what's called a dipole arrow. So there's a pull of electrons towards fluorine. This is called a dipole, or more specifically a bond dipole arrow. Later on, I believe in Unit 7, we're going to learn about molecular dipoles. But these are bond dipoles. Okay, I'm only looking at the bond. Now, if the difference is very, very large, that atom will pull electrons towards it and take electrons, meaning there's a transfer of electrons. For instance, if I had Kf, Kf is really what? K positive with an F minus. Okay? We learned this when we were categorizing types of molecules. This is an ionic compound. And that ionic compound has an ionic bond. All right. All right. Now, before we go back to our notes, we're going to use these electronegativity values to figure out whether we have a nonpolar covalent bond, polar covalent bond, or ionic. Now, if there are some general rules, now these ranges can be a little bit different depending on the source, but in general, if the electronegativities differ by less than 0.5, okay, that's the range from 0 to 0.5, your covalent bond is going to be nonpolar. Okay. Now, think about this. If I have F2, okay, two fluorines, and they are covalently bonded to each other, you see that it's a tie. They're both fluorines. They have equal pull. So the electronegativity difference should be 0. And if we do the math, it's 4.0 minus 4.0 equals 0. Okay? So that bond is what's called a nonpolar covalent. How about a bond between carbon and hydrogen? Okay. And let me just, so we're consistent, we have a molecule, CH4. You could call this carbon tetrahydride from our nomenclature rules. Well, if we take a look at this bond right here, okay, carbon has an electronegativity of 2.5 minus hydrogen, which is 2.1. What is the difference between 2.5 and 2.1? That difference is 0.4. That is still considered nonpolar covalent because of this range right here. You could think of a nonpolar covalent bond as a bond in which the electrons are pretty much equally shared. I know there's a slight difference, but it's close enough that we can consider it equally shared between the two atoms. This is CH4. But if the difference grows, and we have a difference between 0.5 and 2.0, that's called polar covalent. And an example of that is a molecule that we've seen already, hydrofluoric acid. So let's double check that. HF. Okay, put your lone pairs. That bond right there. Okay. F has an electronegativity of 4.0. Hydrogen has an electronegativity of 2.1. That is 1.9. Okay, so it's pretty polar. It's on the higher range of polar covalent bonds. This is called polar covalent. And why don't we prove? Why don't we prove that a KF bond, you could draw it like this if you want, or because we have a metal, right? So this is a rule that you learned quite a while ago. If you have a metal and non-metal, typically you're going to form a ionic bond. But now let's prove it. Because an ionic bond is where the bond is between two atoms where the electronegativities differ by 2 or more. Okay. K, I'm reading from the chart, is 0.8. So F is 4.0. again, minus K, which is 0.8, and that is 3.2. That is an example of an ionic bond. Ionic bond. Okay. Well, now that we know electronegativities better, you may want to print out this chart also, just so you have it as reference. But again, you'll notice trends, and you'll have an intuition about whether a bond is nonpolar or polar covalent. It's definitely going to be nonpolar, right, if the bond is between two atoms that are of the same element, because there's a difference of 0. You should know that carbon-hydrogen bonds are nonpolar. But most other bonds, okay, that you'll see, they're going to be either polar covalent or ionic. Polar covalent or ionic. And let's take a look at the examples that we talked about at the very beginning of this video. Right? PO4 3- and OCN-. I'm going to go a little bit fast because the steps to figure out the Lewis structure have been discussed already. But the first step is go ahead and count the number of valence electrons. 5 plus, see, you'll know that phosphorus is underneath nitrogen. Nitrogen has 5 valence electrons. Same thing with phosphorus. 5 plus 4 oxygens that each have 6 valence electrons. But we have a 3-. We actually added 3 electrons. 24 plus 5 is 29, 32. 32 electrons. Phosphorus is the central atom, but also we could use the same rule. The least electronegative atom is usually the central atom. And we know that oxygen is the second most electronegative atom. Fluorine is the most. So phosphorus has to be the least electronegative atom in this case. And you draw 4 single bonds. What was the next step? The next step was to make all those oxygens fulfill the octet rule. Okay? Make all those oxygens, or make all the outer atoms fulfill the octet rule. Double check that you have the right number of electrons, and we do. Okay, because each phosphorus-oxygen bond has 8 electrons when you include the lone pairs. So that's 8 right there. We have 4 of those situations. Check. But now the formal charge. So the formal charge is going to, you'll see, alert us to a problem. Again, formal charge is the number of valence electrons minus baseball bats, 1, plus baseballs, 6. That's -1. So all of these oxygens are -1. Okay. Well, phosphate is 3-. There must be a plus charge somewhere, and it's this phosphorus. This phosphorus has the valence of 5 minus 4 sticks plus 0 balls, and that's +1. So your plus charge is for this phosphorus. Now, remember the rule that you want to minimize the number of atoms that have charges, if you can. The phosphorus satisfies the octet rule, but the idea that you want to minimize the number of atoms that are charged is overriding that rule, and we will move a lone pair, and we get this Lewis structure now. Negative, negative, negative. What about the phosphorus? Are we sure that phosphorus has no charge now? Phosphorus has a valence of 5 minus 1, 2, 3, 4, 5. 5 sticks, 0 balls. That's net neutral. This is the valid Lewis structure right here. Okay. The phosphorus is hypervalent. Okay, let me take care of this weird one, OCN. But now we have a rule to determine where the central atom is, or what the central atom is. It's the one that is least electronegative. And yes, when you look at the Pauling electronegativity table, carbon is the least out of those 3 elements right there. But you don't need the electronegativity table. You know the trend already. As you go from left to right, it's increasing electronegativity. Let us do OCN. Figure out first the number of valence electrons. 6 plus 4 plus 5. But you have a negative charge, so that's another electron. This has what? 6 plus 6 is 12, plus 4 is 16 electrons. Okay. Central atom is carbon, based on electronegativities. Make a single bond to the outer atoms, oxygen and nitrogen. Make those outer atoms fulfill the octet rule. Okay, make sure you have the right number of valence electrons. 2, 4, 6, 8, 10, 12, 14, 16. Okay, and now the formal charge. The formal charge for oxygen that only has 1 bond and 3 lone pairs is negative. We've done that calculation many times. What about the nitrogen? The nitrogen has a valence of 5 minus sticks plus balls. Ooh, 5 minus 7. So that's not good. That's a negative 2. So we'll put here a 2 minus. Okay. I bet carbon's going to be wacky as well. Carbon has a valence of 4 minus, oh boy, 2 plus 0. That equals plus 2. So this is 2 plus. Couple things. Carbon is not a period 3 element. The period 3 elements can have expanded octets, or can be what I call hypervalent, but carbon cannot. Carbon should satisfy the octet rule. So carbon has to satisfy octet rule. There is one exception, but we're not going to go over that. For now, try to make carbon satisfy the octet rule. So how are we going to move the electrons? Okay. Not only that, we got to get rid of. So there are 2 things we got to accomplish. We got to make sure that carbon satisfies the octet rule, but we got to get rid of the 2 plus and the 2 minus as well. Right? That was one of the rules, that we shouldn't have anything more than a plus 1 or anything less than a minus 1. If I move that lone pair, okay, if I move that lone pair, I make carbon plus 1 and I make nitrogen minus 1. So it takes practice and it takes some familiarity, but I'm going to move both lone pairs, 2 lone pairs. Now, it's going to come with practice, and the more examples you see, the easier this will be. But this is one of those really unique examples where I would at first try to memorize it. But see if this trial and error works. So my trial is going to be moving these 2 lone pairs. I have O, C. Now we have a triple bond because I moved 4 electrons, N. There's a lone pair left over. Okay, good. And then our oxygen is still like this. Okay. That carbon is neutral. That nitrogen, we could double check. 5 minus 3 sticks plus 2 balls equals neutral. This is the valid and preferred. Okay. Now, some of you I know have been experimenting and may be asking, well, let's start again from the beginning. And now let's move the lone pair of oxygen. Why do we move the lone pair of nitrogen? Because I really got to get rid of this 2 minus. But let's say, let me try to get rid of this 1 minus, because it's still good to have less atoms that are charged. So we have this. Okay. The thing is, I'm not taking care of this nitrogen. I'm not taking care of this nitrogen. It's still a 2 minus. Alright, so let me do this. Look at the result. The result is O with a double bond to carbon, carbon with a double bond to nitrogen. You have 2 lone pairs for oxygen, still 2 lone pairs for nitrogen. Where's the charge? The charge is here. N has 5 valence electrons minus 2 sticks plus 4 balls equals -1. Oxygen and carbon are neutral in this case. So take a look at these two. Okay. They look great. Carbon in both cases fulfill the octet rule. We got all the charges gone except for one, but we need a charge because this ion has a negative charge. The only difference between these two is the location of the charge. So if everything equal between 2 Lewis structures, this is an important rule, between 2 Lewis structures, except for what? Except for the location of the negative charge. Then you will pick the Lewis structure that has negative charge on the more electronegative atom. Pick structure with a negative charge on the more electronegative atom. This is a valid Lewis structure. This is a valid Lewis structure as well, but less preferred. What does that mean in terms of doing this on an exam? It will be hopefully obvious whether your professor wants you to draw all the valid Lewis structures or whether your professor wants to ask you what is the most preferred or the most valid Lewis structure, and it would be this one, the one I'm pointing at. Okay, it's a rule that we haven't seen, probably not until now, but we need to know electronegativities because, again, if everything being equal, right, the number of atoms that are charged, the number of atoms that fulfill the octet rule, if all of that is equal between 2 Lewis structures except for the location of the negative charge, then pick the structure that has a negative charge on the more electronegative atom because that electronegative atom can accommodate that charge. It's more comfortable accommodating that charge. So oxygen is more comfortable being negative than nitrogen is. And comfortable meaning stable.